My name is Bruno. I am the author of the paper titled Sensitivity of Barkhausen Noise Measurement on Steel Samples, produced by laser powder bed fusion, developed together with my colleagues Lima, Oliveira, Robato, and Rego from the Aeronautics Institute of Technology. The statistical understanding of the variability in magnetic Barkhausen noise signal, which is sensitive to the stress state and hardness of the material, is capable of providing a non-destructive method for a comparative evaluation of the residual stress state in steel samples. The objective of the present work is to determine factors that influence the uncertainty of the signal, such as the sensor positioning, the contact area of the sensor, and some intrinsic differences between operators when measuring. The study was conducted using repeatability tests, which aim to analyze the variation of the signal as a function of the method itself. Reproducibility tests, which aim to identify variations caused by the operators, and the test of the surface contact area of the sensor with the sample, in order to investigate the variation as a function of the contact area. But first, let us understand how the magnetic Barkhausen noise phenomenon and technique of measurement works. The ambient phenomenon happens by inducing discontinuous changes in the magnetization of ferromagnetic materials under the influence of a continuously variable magnetic field. The output from this effect, which is the signal strength, is directly affected by the hardness and residual stress of the material being evaluated. So the Barkhausen noise technique is emerging as a highly capable method of evaluating microstructural parameters in real time due to its non-destructive characteristic. Then there is a real need for a quantitative understanding of the correlations between parameters that influence the Barkhausen noise signal that are not correlated to the material. In the current days towards which the automotive industry is heading, electric vehicles are gaining the spotlight, and with them, new drivetrain concepts are needed to overcome the challenge of system efficiency, noise, and vibration. The additive manufacturing may be the solution to overcome the limitations of conventional manufacturing processes, with its benefits of geometric freedom and new material possibilities. However, additive manufacturing processes such as laser powder bed fusion induce heterogeneous microstructure and residual stress that may impact the mechanical performance of the components. The present study, therefore, aims to study the main parameters that influence signal strength, comprising an analysis with different operators and different measurement conditions. Repeatability and reproducibility tests collaborate to increase the spectrum of non-destructive surface inspect solutions, helping to investigate the robustness of the signal. Therefore, this study, which aims to analyze the sensitivity of the signal, also contributes to further research on the surface integrity of additive manufacturing samples. I will approach the materials and methods sections in the way that is divided into three parts. We will discuss the equipment used for the measurements, the samples used in the test, and the method of measurement. First, the ambient analysis requires the use of a Barkhausen noise signal analyzer and sensor, which is the stress-tech Roscam. The equipment is used for controlling surface quality and investigating near-surface defects in terms of residual stress and microstructural changes. The measurement process starts inducing an alternating magnetic field, which tries to align the magnetic domains to the material in the direction of the field. This sudden change in the magnetization induces electric pulses, which are called Barkhausen jumps. These jumps captured by the Roscam, which is amplified, filtered, and displayed on the device screen. The range of the equipment settings used for the Barkhausen noise measurements include the waveform, the voltage and the frequency of magnetization, the filter of the signal, and the output is displayed in terms of magnetoelastic parameter. With 3 specimens of additive manufacturing made with laser powder bed fusion technology, which are 2 rods and 1 gear, the spur gear used for the measurement has 21 teeth, 2.85 millimeters of normal module, 20 manganese chromium 5 is the material, and the metal powder has a medium size of 29 micrometer. The 2 rod samples have a diameter of 9.53 millimeters and a length of 76.2 millimeters. The laser power bed fusion process was performed in the Alchemist Laser Foam 200 machine with a 200 watts of power, 550 millimeters per second of scanning speed, 0.1 of hatch spacing, and a power bed of 100 degrees Celsius, a deposition angle of 14 degrees, and the filling strategy was islands of 5 millimeters. In order to estimate the repeatability and reproducibility of measurements with the Barkhausen noise sensor, the experimental procedure was developed to observe the variation due to the measuring process when the operator measures the same part several times, and to observe the variation due to the method itself by comparing the results of the 3 different operators. First, in the repeatability test, the operator measured the 21 tooth gear sample in 3 series of test repetitions, N1, N2, and N3. To also ensure the randomization of measurements, the order of measurement of the flanks was randomly defined for each operator. Repeatability tests were also performed on the rod samples. The procedure followed the same logic for the 2 rod samples. Each operator had to measure the specific region 3 times in 3 series of repetitions, N1, N2, and N3. The reproducibility test was developed to compare the variation of results between 3 operators. And to achieve this goal, it was defined that each operator would perform 10 measurements on each sample in identical predetermined regions. 10 measurements were performed in region T2 and in the laser bed powder fusion gear, 10 measurements in the region B3 in the rod as built, and 10 more measurements in the region B1 in the other rod stress relief, totaling 30 measurements for each operator. To estimate the quantification of its influence, the sensor contact area was varied on a flat ferromagnetic surface to block its area of operation in terms of the ideal measurement area. The variation of the contact area of the sensor with the sample was performed as a function of the center line of the sensor. The contact was blocked using a insulating rubber-based adhesive tape, and for these tests, the contact area was varied as a function of the percentage of the sensor surface area in contact with the sample. These tests were divided into 100%, where the sensor surface area is completely in contact with the sample, 50%, 25%, and 0%, where the sensor surface area is completely obstructed by the rubber-based adhesive tape. The radial graph illustrates the geometry of the gear, and it can be seen that not only there are points with greater signal divergence between the 3 measurements, but also regions of the sample with different absolute values. The results demonstrate that the difficulties of repeating the measurements on a complex geometry, as well as the metallurgical differences that influence the magnitude and variability of the signal. In the measurements performed on the gear, The largest standard deviation found was the 212 region, caused largely by the disagreement between the N1 test series and the N2 and N3 series, which yielded close results. For the results of the two rod samples, the larger standard deviation are caused by the divergence between the first series of measurement and the other two, showing the signal uncertainty even in a more controlled geometry. But to better illustrate the results, the average of the repeatability test was expressed in terms of the percentage of standard deviation here. And the first evidence in terms of change in the sensitivity of the Barkhausen noise signal occurs when it's considered the presence of involute geometry on the flank of the first sample, whose signal sensitivity was 20% higher than in the rod samples. This fact demonstrates that factors such as the sensor's contact area with the sample surface and the positioning of the sensor itself can cause significant signal deviations in the results. Observing the results for each operator, it can be seen that the greatest variation of the signal in the sample with involute geometry is a trend, and showing the difficulty of measuring due to geometry. The maximum value of the standard deviation for the gear sample is 92, and the minimum value of standard deviation is 18. For the first rod sample, it can be seen that there has a divergence in the first measurement for the one of the operators, and the maximum value of the standard deviation is 75, and the minimum is 12. For the second rod sample, the minimum standard deviation is 1, and the maximum is 28, showing that the surface geometry is a very important parameter when evaluating the statistical variation of the Barkhausen signal. And summarizing the results in three tables that are related to the absolute mean of the signal to the standard deviation, it can be seen that the rod geometry contributes to the signal having less variability, and it can be estimated that the variability of the gear contributes to the signal deviation being almost double that of the rod samples. When evaluating the average of the values as a function of the contact area of the sensor with the surface, it is noticed that the parameter directly influences the measurements in a long, linear way. This is observed when comparing the values of the sensor completely in contact of the surface with the measurement values with the sensor completely blocked, whose value is not null, representing 56% of the total value on average. So it is found that having the control of the area of the contact of the sensor in the sample is a very important parameter, showing that the signal may drop in half when not having ideal position while measuring. For the conclusion of this study, three factors gained the spotlight when evaluating the variability of the Barkhausen noise signal: positioning of the sensor, complex geometries, and different operators. In the reproducibility test, an average difference of 16% of the maximum and the minimum values were found between operators was identified, showing that it is essential to certify whether the expected values for materials failures overlap this tolerance. Future work should propose the investigation of the Barkhausen noise signal combined with residual stress tests that will serve to demonstrate the signal difference found and perform a comparative analysis between parameters that influence the measurement with regions of metallurgical divergence that also influence the Barkhausen signal. It is expected that this study may allow future studies in the field of identification and investigation of gear failures using the Barkhausen noise technique. And for the continuation of this study, new parameters that can influence the measurements will be evaluated in order to contribute to the Barkhausen noise method for early failure detection in gears. The authors gratefully acknowledge the support of the Programa Voluntário de Iniciação Científica do ITA, PVIC-ITA, for the conducted research, and the Alchemate Technologia for the support with